Hey everyone, thank you for tuning in. My name is Bharath. Today I'm going to be talking about the open source project called as k0rdent. A little bit about me. I'm in the open source program office in Verantis, and I'm a senior software engineer. I've been in the industry for almost 8 years now, and half of that has gone into in and around Kubernetes and the ecosystem. Let's talk about that. So Kubernetes on cloud was supposed to be this promise of making everything good and easy. Of course, things got really complex as the Kubernetes and its surrounding ecosystem matured. And as you can see, the interactivity between different components and the APIs and stuff became really complicated, right? And thus the need for platform engineering. Today's world, I can't even say the future as it notes on the slide, but already today, more and more things are becoming AI centric. And no matter what you do, no matter what business you're in, eventually AI is going to be the bedrock of things moving forward. So this is where we see Kubernetes being a very, very powerful utility, a tool, a platform, and an ecosystem to handle all your AI workloads and applications. Just to talk about the enterprise requirements for platform engineering, right? What do people look when they talk about platform engineering? Most importantly, we always mention something called a self-service platform for the developers, wherein today, if you need a cluster on let's say AWS or Azure or whatever cloud your company is using, you got to create a ticket because what's life without tickets, right? And then you have to wait for the corresponding DevOps team or whoever is taking care to go ahead and provision the clusters for you, which could take like hours or days and then get back to you with the actual cluster. This is a very important part where platform engineering is a very good possible solution. Developer directly themselves access, a web application or something like that, fill up the information that they need, and then a cluster is provisioned on the cloud, and then that's already delivered to them. One more thing I want to mention here is the security and compliance. So you have to shift left when it comes to security. We've been hearing this word, and it's really important because when you're designing a platform engineering team or a platform, you have to remember that the underlying security principles are extremely important, without which the area for compromise becomes really big and it goes out of control. So according to the survey, right, 79% of organizations, not just huge enterprises, but even small and medium scale businesses, have multi-cloud in their, DevOps or platform engineering premise. But only 29% of them have adopted platform engineering best practices, to manage these effectively. So going forward, be it like two clusters or 2000 clusters, right? Multi-cloud, multi-cluster is becoming the norm, right? And when this is so, how can you solve this problem? What can you do about it, right? Of course, the easy thing is to do nothing, but we all quickly know that that will accumulate your tech debt and one day it'll explode. And the other solution is to go for the open source DIY solution. Of course, Kubernetes is what it is today because of the amazing open source communities and projects and products and tools and technologies, everything in and around it. So it's very nice. But then when you actually go ahead and try to implement it in your enterprise, you'll soon realize that it's a lot of pick and choose from a lot of technologies, and it'll become complicated for you to manage it. Then there's a proprietary solution. So of course, this is great. So if I'm using AWS or Azure or VMware or any other cloud out there, either it's on-prem solution or on-cloud solution, you have good solutions. But the challenge with this becomes, the vendor lock-in thing. So we've all seen what's happened with the Broadcom acquisition of VMware, just to pick out a big example, but there have been multiple similar examples at different scales as well, where nobody wants to get into this vendor locking solution, right? And then there's the enterprise grade open source solution, which is what I want to talk about today, where Open source technologies are chosen, curated, tailored, and then an entire suite, an entire platform is given as a solution. That's where Cordant comes in, right? So Cordant primarily is composed of three things: cluster management, state management, and observability. Talking about observability first, it's basically this unified dashboard which tracks metrics across your clusters, and then presents it to you. Cluster management is the day zero cluster provisioning stuff. This component is the thing that takes care of actually provisioning clusters for you across clouds. State management becomes your day two stuff, where you're talking about deploying applications and templates across your clusters seamlessly. Just a brief, so this is the entire stack that Cordon promises to provide. The bottommost stack being the infrastructure providers, and the topmost stack being the application management, observability stack, and all that, and the middle part being taken care by Cordon. So I mentioned it uses open source technologies, right? Let's briefly look at what kind of components are there in each of the components I mentioned earlier. So the cluster management is completely handled by the upstream CAPI. So just to mention, CAPI is the cluster API. This is the project under Kubernetes 6. This is the standard and accepted, widely used way to provision a cluster. And all providers have their own controllers, developed in order to work with the upstream CAPI controllers. And that's why we have CapEx controllers like Kappa for AWS, CapZ for Azure, Capo for OpenStack, and so on, right? And then there's the Cosmotron controller, which is basically the control plane for managing and deploying Kubernetes clusters. While that's the cluster management, the state management is handled by yet another open source project called as Sveltos. This is responsible for actually deploying and managing application workloads across your clusters. This whole thing is handled by a custom resource in Kotlin called as cluster deployment, which consists of cluster template for cluster and service template for services, right? We'll soon see an example. So maybe I'll jump a little more into them when we see the example. Now talking about AI. So I tried to lay a foundation for platform engineering, and then let's jump into AI, right? So AI isn't just about models. It's not about how fast or how smart and intelligent the models are. It would be like almost useless if you don't take care of the underlying infrastructure and make that robust and better suited to serve those models, right? And this is where Kubernetes comes into picture. It's not just good for AI, it's really ideal because a lot of things that you would implement individually, if you were dealing with a bare metal or a server solution, is sort of taken care by Kubernetes, right? If I take an example of auto scaling, Kubernetes has always had the solution, be it AI workloads or not, and we can extend that solution, right? So this is the example I mentioned, cluster deployment, cluster template, and service templates, right? For our AI-ready Kubernetes cluster, and the example I'll show you, these are the services that we need. GPU operator in order to tell the underlying cluster that this is in fact a GPU-enabled cluster, and that installs the required dependencies. Cert manager for certs, Istio for routes, Knative and KServe for the actual scaling of the AI applications. So all this is defined in just one single YAML file, and that's that. So just to quickly mention, the cluster templates would be available as such on your cluster and service templates as such. So we've created a catalog for service templates wherein any service that has a Helm chart, and most of them do, and even if you don't, you can develop your own Helm chart, can be installed as a service template. So the service template will simply reference the corresponding Helm chart. So let's take a look at our actual cluster deployment, right? So the left side specifies the cluster config and the right side specifies the services. So the service spec, as you can see, lists all the services that we've talked about and just references the template. And the cluster config talks about the template to be used and the configuration of your control plane and the worker node. And then here, if you can see, the VM size that's used for the worker is actually a Tesla T4 GPUs, right? And this is the provision cluster. So we just have to apply this cluster deployment like we do kubectl apply, and then the resulting, we have a cluster on Azure that's deployed. And while the cluster is the date zero part that I talked about, the day two part comes here. So because we specified the services in the service spec in the cluster deployment, we now have the NVIDIA operator being deployed in its namespace and the rest of them in the corresponding namespaces as well. Cert Manager, Istio, Knative, and KServe, right? So all this is done by just applying the cluster deployment, without which you would have to manually deploy each and every service, configure them, and so on. Now, coming to the use case that I want to show, just to get your feel of how this would actually work. Now that we've developed the platform for it, I'm using KServe's inference services. It's a custom resource from KServe. I've deployed three of them: Cubespra, LexiShift, and Voxraga. And then there is a pipeline application, Noodle Babel, right? So inference service spawns up pods. And what this is going to do is translate speech from one language to another, right? So as you can see, I just need to deploy the inference services and that automatically spawns the pods. While I send my actual requests, KServe has the inherent capability to spin up the pods, maintain either one replica or two or three, depending on the annotations that we have given in the inference service YAML. And this is the power. When the real request comes in from the user, the pod is spun up, and then the request is served, and then the pod is again spawned back down. That is totally under your control. You can even put it back to zero if you don't want your CPU resources to be consumed, or you can put it to one to keep it at one minimum, and then KServe will take care of the rest, right? So this is the power of using a tool like k0rdent, where the entire spec of your cluster spec and then of your service spec is completely defined within one YAML. It is extendable. You can patch it up to upgrade, let's say, for example, a newer version of Cert Manager, and it deploys across the clusters that you mentioned, right? So there is a website called as catalog.k0rdent.com, which specifies all the service templates that are there in the market, and you can contribute to it as well. So thank you so much for tuning in. Thank you for listening, and I'd appreciate it if you can go and check it out and try it yourself. k0rdent.io is the website, and k0s project.io is the underlying k0s distro as well. Thank you. Cheers.